The cosmos contains more stars than every grain of sand on every beach on Earth. Each of those stars could host worlds, and the numbers suggest life should be everywhere. So why does the universe feel so utterly, completely silent? This is the heart of the Fermi paradox, the glaring contradiction between a universe that should be teeming with voices and the profound quiet we actually observe. It is like walking into the grandest library imaginable, shelves stretching to infinity, only to discover every single book is filled with blank pages. By the end of this exploration, you will understand the most compelling scientific ideas that attempt to solve this ultimate cosmic mystery, from the terrifying concept of a great filter to the possibility we are living in a galactic zoo. We will investigate if the silence means we are tragically alone, dangerously early, or simply not listening correctly. What does this vast and quiet universe make you feel about our own place within it? That sense of walking into an empty library begins with a simple, almost incomprehensible number. Our home galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. To grasp that, picture every single grain of sand on every beach and in every desert across our entire planet. That vast collection of sand grains represents the stars in just our galaxy. Now consider that the observable universe holds perhaps 2 trillion galaxies. The numbers become not just large but meaningless to our human minds. They are a foundation of pure, staggering potential. To make sense of this potential, scientists created a framework. It is called the Drake equation, named for astronomer Frank Drake, who first wrote it down in 1961. It is not a formula with one answer, but a way of structuring our ignorance. The equation is a chain of probabilities. It starts with the rate at which new stars form in our galaxy. Then it asks what fraction of those stars have planets. Of those planetary systems, how many have a world in the just right zone where liquid water could exist? On those suitable worlds, how often does life actually begin? Once life begins, how often does it evolve into intelligent, complex beings? And of those intelligent species, how many develop the technology to broadcast their presence across the stars? Finally, how long do those communicative civilizations last before they fade away? When you take even the most cautious, pessimistic estimates for each of those steps and multiply them together, something remarkable happens. The result is rarely 0. Often, it is a number greater than 1, suggesting that even in our modest Milky Way, we should have company. The legendary astronomer Carl Sagan was a powerful voice for this perspective. He argued that in a cosmos so vast with so many opportunities, the idea that we are a solitary accident is far less plausible than the idea that life is a natural cosmic phenomenon. The universe, in his view, seemed to be leaning toward life. This mathematical optimism creates the very heart of the tension. If the numbers whisper that we should not be alone, then the silence we hear is not just quiet. It is a signal in itself. It becomes a profound question mark hanging over everything we think we know. Does this silence mean we have overestimated our own significance, that life is far more fragile and rare than the equation suggests? Or does it mean we are missing something fundamental, a hidden term in the cosmic calculation that explains the great quiet? The sheer scale of the universe promises a chorus, but we hear only a single voice, our own, echoing back at us. This disconnect forces us to look not just outward but inward, and to question the very tools we use to listen. That single voice echoing back at us forces a humbling question. What if the universe is not empty, but we are simply the first ones to arrive at the party, or the last ones left? This leads us to the first compelling resolution of the Great Silence, an idea that turns our gaze from the stars back to our own world. It asks us to see Earth not as a typical planet, but as a cosmic jackpot winner. This is the rare Earth hypothesis. To understand it, we must rewind our own planetary story to its most violent, formative moment. Not long after Earth coalesced from the dust of the young solar system, a smaller, Mars-sized world is believed to have smashed into it. This catastrophic collision did not destroy our planet, but utterly remade it. The debris from this impact coalesced in orbit, giving birth to our moon, and that moon, so large relative to its parent planet, became our silent guardian. Its gravitational pull acts as a steadying hand on Earth's spin, preventing the wild, chaotic wobbles that would cause extreme climate swings over millions of years. Without our large moon, Earth's tilt could vary dramatically, turning our stable seasons into a roller coaster of climatic chaos where complex life would struggle to gain a foothold. But a stable climate is just one line on a very long list of requirements. Look further out in our solar system to the gas giant Jupiter. Its immense gravity acts as a cosmic vacuum cleaner, drawing in or deflecting countless comets and asteroids that might otherwise rain down on the inner planets. While some impacts are necessary, like the one that may have delivered water, a constant bombardment would be a recipe for extinction. Jupiter serves as a protective shield, allowing life on Earth the relative peace to evolve. Then look beneath our feet. The very ground we stand on is alive, slowly churning. Plate tectonics, the movement of continental slabs, is not just the cause of earthquakes and mountains. It is a global recycling program crucial for life. This process pulls carbon from the atmosphere, locking it into rock, and then releases it back through volcanoes over geological time. This planetary thermostat has helped regulate Earth's temperature for billions of years, preventing a runaway greenhouse effect like on Venus or a deep freeze like on Mars. It also constantly renews the nutrients in the crust and oceans, fueling the chemical cycles that life depends on. Our neighboring planets, Mars and Venus, show us what happens when just a few of these conditions go wrong. Mars, too small to maintain a strong atmosphere and a magnetic field, saw its water vanish into space or freeze underground. Venus, closer to the Sun and trapped in a runaway greenhouse effect, became a scorching, acidic pressure cooker. They are not evil twins, but natural experiments in planetary evolution that failed to sustain the delicate, long-term balance Earth achieved. Scientists like Peter Ward and Donald Brownlee argue that this balance is not common. It is exceptionally rare. The list of necessities is daunting, a perfect storm of galactic location, star type, planetary size, composition, orbital dynamics, and sheer geological luck. If the rare Earth hypothesis is correct, then planets with complex animal life, let alone intelligent technological civilizations, might be scattered as infrequently as single grains of sand across an entire continent. This idea offers a clean, if lonely, answer to the Fermi paradox. The universe is silent not because civilizations destroy themselves, but because they almost never arise in the first place. We are not hearing from others because there are essentially no others to hear from. Earth is the fluke, the one in a trillion. But does this truly resolve the paradox, or does it merely push the mystery back a step? It asks us to accept that in a cosmos of 2 trillion galaxies, the chain of events that led to us happened exactly once. For some, that feels like a profound insight into our fragility and good fortune. For others, it feels like a statistical surrender, a giving up on the promise of the cosmos too soon. It forces us to confront a deeper uncertainty, one not about the conditions for life, but about life's own tenacity once it does begin. But if Earth is not a miraculous fluke, if life truly is a natural cosmic phenomenon, then the silence becomes far more unsettling. It suggests something is actively preventing civilizations from making their presence known. This leads us to the second, and perhaps most haunting, resolution to the paradox, a concept known as the Great Filter. picture evolution from stardust to starfaring civilization as a long and perilous obstacle course. The Great Filter is that one nearly impassable barrier, a stage so difficult that almost every competitor fails. It is a cosmic bottleneck that explains the eerie quiet. The true terror of this idea lies in its ambiguity. We do not know where on the course this filter is located. There are only two possibilities, and one of them carries a dire warning for our own future. The first, more comforting possibility is that the filter is behind us. It is a step we have already passed, a hurdle so astronomically rare that we are among the tiny few who cleared it. Perhaps the initial spark of life from non-living chemistry is the filter, or maybe the leap from simple single-celled organisms to complex, multicellular life represents a biological barrier that most worlds never cross. If this is true, it means the galaxy could be filled with silent, microbial worlds, ponds of primordial soup where evolution stalled forever. We, having passed this ancient filter, might then be destined to find only fossils and bacteria as we explore the cosmos. The silence is not ominous, it is simply biological. The second possibility is the one that keeps scientists and philosophers awake at night. What if the Great Filter is still ahead of us? This is the scenario where the development of intelligent life is common, and the emergence of basic technology is not particularly rare. The filter, then, is what comes next. It is the perilous transition from a species that can build radio telescopes to one that can sustainably exist across millennia, a phase we might call our technological adolescence. The very tools that signal our presence, nuclear energy, artificial intelligence, advanced bioengineering, could become the instruments of our own undoing. Historian and economist Robin Hanson, who helped popularize this theory, frames it with stark logic. If we see no great galactic civilizations, he argues, then something must be preventing them from arising. And if that something is not in the distant past, it must be in the near future, a future that awaits every species like our own. We can look to our own human history for a sobering parallel. Consider isolated island civilizations on Earth that developed in splendid isolation. When more technologically advanced explorers finally arrived, the results were often catastrophic for the isolated culture, not through malice, but through disease, social disruption, and sheer cultural shock. In the cosmic version of this story, we are the isolated island. The filter may be that moment of first contact with a superior intelligence, or more likely, the moment a civilization gains the power to alter its own planet or genome fundamentally, and then makes a single, irreversible mistake. So here is the chilling question the Great Filter forces us to ask ourselves: which scenario would you prefer to be true? Would you rather live in a universe where the miracle has already happened, where we are lucky survivors of an ancient evolutionary lottery? Or would you choose the universe where we are pioneers on the brink, where the great silence is a warning sign posted at the edge of a cliff we have not yet seen? The anxiety of a future filter forces us to look squarely at the dangers of our own growing power, and to wonder if the very ambition to reach the stars contains the seed of our own end. The idea of a future filter is a heavy one, but it is not the only way to interpret the silence. There is a third possibility, one that replaces cosmic danger with cosmic curiosity. Imagine a vast, pristine wildlife sanctuary. Within its borders, rare and delicate ecosystems are allowed to flourish, untouched by outside influence. Observers watch from hidden platforms, careful not to disturb the natural behaviors unfolding below. Now, extend that image to a galactic scale. What if Earth is that sanctuary, and we are the observed species? This is the core of the zoo hypothesis, sometimes called the planetarium hypothesis. It proposes that advanced civilizations are fully aware of our existence, but have chosen to place us under a kind of cosmic quarantine, a directive of non-interference. Our planet is a protected exhibit, and the profound silence we perceive is not emptiness but the sound of disciplined observation. The concept borrows from our own human protocols. Anthropologists and governments have established policies of no contact with the few remaining uncontacted tribes deep in places like the Amazon or the Andaman Islands. The reasoning is ethical: to protect these communities from diseases their immune systems cannot fight, and to preserve their cultural autonomy, allowing their way of life to evolve without external shock. From the tribe's perspective, the wider world might as well not exist. They have no evidence of its cities or technologies, living in a bubble of intentional isolation. If a galactic community exists, they might operate under a similar but far more advanced ethical framework, a sort of interstellar prime directive not born of law, but of a matured wisdom that understands the value of undisturbed development. What could motivate such a policy? Scientific curiosity is the simplest answer. We are a living record of a technological civilization's infancy, a priceless case study in societal and technological evolution. To interfere would be to ruin the experiment. Another motivation could be protection, a benevolent desire to shield a young species from the potential dangers or corruptions of a wider galactic society until we are mature enough to handle such knowledge. There is even an aesthetic possibility that our world in its current state is valued as a form of living art, a dynamic, evolving masterpiece to be appreciated from afar. The silence, then, is not a sign of absence but of immense respect. This theory invites a deeply personal reflection. How does this idea make you feel? Does it offer a comforting sense of being watched over, of having guardians in the dark? Or does it instill a claustrophobic sense of being trapped in a cage, your entire history and future predetermined as part of some grand, unknown curriculum? Are we free agents shaping our own destiny, or are we characters in a story whose authors we will never meet? The zoo hypothesis transforms the universe from a lonely desert into a crowded gallery where every other visitor is holding their breath. It suggests the problem is not that we cannot find anyone, but that everyone is too polite to say hello. This notion of a deliberate, engineered quiet prepares us to shift our perspective once more, to consider if the explanation might be far less about intention and far more about the simple, physical difficulty of the task itself. Perhaps the ultimate answer to the silence is not that civilizations die out, but that they graduate. They evolve into something we can no longer see or comprehend. This is the startling premise of the Transcension Hypothesis, a concept championed by futurist John Smart. It suggests that the natural trajectory for any sufficiently advanced intelligence is not to spread outward across the galaxy in massive starships, but to turn inward, to transcend the physical realm we inhabit. Think of it as a technological and evolutionary singularity, not just for artificial intelligence, but for an entire civilization's way of being. The driving force, according to this idea, is a universal pressure toward efficiency. As intelligence grows, it seeks faster processing, denser information storage, and greater energy efficiency. The physical universe, with its vast empty spaces and slow speed of light, becomes a frustratingly clunky and inefficient environment. Why build colossal Dyson spheres around stars when you could achieve vastly more profound experiences within a reality of your own creation, operating at the scale of atoms or even fundamental particles? The hypothesis proposes that advanced beings don't vanish, they miniaturize. They might migrate their consciousness into incredibly dense, complex substrates, perhaps within the energetic frontiers of black holes or into domains of physics we have not yet discovered. To us, their civilization would appear to have simply winked out of existence. They have not died, they have moved into the basement of reality, and we are still upstairs, unaware of the universe humming beneath our feet. A simple analogy helps frame this. Picture an ant colony thriving in a patch of forest. The ants are aware of the sun, the rain, the soil, and the leaves. They go about their intricate lives, yet buried deep beneath their colony are fiber optic cables carrying the entire internet. The ants have no framework, no sensors, to even perceive this vast, hyper-fast network of information and communication that exists literally within their world. They are not primitive, they are simply operating on a different scale and within a different paradigm. The Transcension Hypothesis applies this logic to the cosmos. The silent universe we observe may not be an empty house, but one where all the other residents have moved into a more advanced, integrated, and invisible part of the structure. They have left the messy, material kitchen behind for a sleek, digital living room we cannot find the door to. This leads to a profound and strangely beautiful question. Could the ultimate fate of all intelligence be to disappear from the cosmic stage, not with a bang, but with a quiet transformation into something sublime and undetectable? It reframes the great silence not as a cemetery, but as a graduation hall. Everyone else has already received their diploma and moved on to realms beyond our current science, even beyond our imagination. This idea forces a humbling focus on the limitations of our own perception. We are searching for radio signals and optical signatures, looking for versions of ourselves that build things big and bright. But what if everyone who makes it that far quickly learns that the real action, the real meaning, lies in a direction we are only beginning to glimpse, in the realm of the infinitesimally small and the virtually infinite? It suggests the universe might be teeming with intelligence, but we are like a person trying to listen to a symphony by pressing their ear against a wall, missing the music because we are listening to the wrong frequency, in the wrong dimension. The vast ocean of space is not just wide, it is unimaginably deep in time. Our search for signals assumes a conversation, but what if every civilization only speaks for a moment? This is the brief window theory, a resolution built on cosmic bad timing. Think of two ships lost in an immense, foggy ocean. Each captain, alone and hopeful, occasionally blinks their powerful light into the gloom, a random pulse against the darkness. The chances that one ship's blink will happen at the exact moment the other is looking in that precise direction are vanishingly small. Now scale that ocean to a galaxy 100,000 light-years across and replace minutes with millennia. The theory suggests that the period when a civilization is both technologically capable of broadcasting detectable signals and actually choosing to do so might be astonishingly brief, perhaps just a few centuries in a cosmos billions of years old. After that, they may transition, as our Transcension Hypothesis suggested, to technologies we cannot perceive, like tight-beam laser communication or quantum networks, or they may simply turn their focus inward. Our own history provides a stark, self-imposed example. For about 100 years, Earth has been leaking a bubble of radio and television signals into space, a growing sphere of noise announcing our presence. But that bubble is already beginning to collapse. The shift from powerful broadcast towers to digital cable, fiber optics, and directed satellite streams means our planetary radio signature is growing fainter with each passing decade. To a distant observer, the bright flare of our 20th century broadcast era might already be dimming, a short-lived blip in the geological record. Now layer on the staggering timescales. The Milky Way galaxy is roughly 13 billion years old. If another civilization had its own century-long period of radio broadcasts, say 2 million years ago, those signals have already washed past our solar system like a wave we missed. If a civilization will have its brief window 2 million years in the future, we are hopelessly early for the party. The odds of two technological species existing within even a few thousand years of each other, within detectable range, and both actively broadcasting and listening in the right direction, start to feel like winning the lottery 10 times in a row. This transforms the silence from a permanent condition into a problem of synchronization. We are not alone in an empty theater. We are all actors performing soliloquies on a stage so vast that our monologues are separated by eons. Our most powerful telescopes might be listening to a channel where the programming aired millions of years ago, or is not scheduled to begin for millions more. This realization forces a critical examination of our search strategy. If the window is so brief, is our current method of scanning the sky for steady, deliberate signals like a continuous beacon the right approach? Or should we be looking for the brief, brilliant flashes, the technological equivalent of a camera's flash going off once in the dark, a signature that might be easier to produce and harder to miss? The brief window theory offers a blend of melancholy and hope. It implies the galaxy could be dotted with the archaeological ghosts of past civilizations, their messages long since faded into the cosmic background static, and the quiet promise of others yet to awaken. Our task, then, is not just to listen for a voice, but to hope our own fleeting whisper happens to cross paths with another in the endless night. Our search for that fleeting whisper in the dark has a name and a very specific method. For decades, the search for extraterrestrial intelligence, or SETI, has been listening. Its foundational strategy is elegant in its simplicity: to scan the heavens for a narrowband radio signal, a focused beam of energy on one specific frequency. It is the equivalent of listening for a deliberate, clear whistle in a cacophonous windstorm. This approach is built on a reasonable assumption that radio waves are a universal, efficient way to communicate across the interstellar void, and that an advanced civilization might use them to send a deliberate beacon, a cosmic hello. But this entire paradigm rests on a single, profound assumption: that an alien intelligence would choose to communicate in a way that we, with our mid-20th century technology, can easily recognize. What if we are not just listening for a needle in a haystack, but we are using the wrong definition of a needle entirely? This is the central challenge facing modern SETI, and it has spurred a dramatic expansion in what scientists call the search for technosignatures. A technosignature is any detectable sign of past or present technology. It moves the search beyond a deliberate message and into the realm of looking for the unavoidable side effects of an advanced civilization. Imagine looking at a distant city not by searching for its radio stations, but by spotting the glow of its streetlights against the night, or detecting the unique chemical fingerprint of its industrial pollution in the atmosphere. Scientists like the pioneering Jill Tarter have long advocated for this broader view. The possibilities are as fascinating as they are diverse. We could search for powerful, pulsed laser signals, far more efficient and focused than radio for point-to-point communication between stars. We could look for evidence of megastructures like the theorized Dyson sphere, a vast swarm of energy collecting satellites around a star that would cause its light to dim in an unnatural, telltale way. Our telescopes are now sophisticated enough to analyze the atmospheres of exoplanets. Could we detect artificial gases like chlorofluorocarbons that have no natural source and would indicate industrial activity? Or perhaps we might spot the infrared signature of a vast interstellar spacecraft, or the waste heat from a civilization's immense energy use. The shift to technosignatures acknowledges the sheer vastness of the cosmic haystack. This haystack is not just space, it is a multidimensional problem. We must search across a colossal range of radio frequencies. We must point our telescopes in the right direction at the right time. And we must consider how a signal might be modulated or encoded in ways we haven't anticipated. A signal meant for local communication within a civilization might be compressed, encrypted, or sent via a medium we haven't even discovered, making it look like random noise to our instruments. The famous WOW signal detected in 1977 exemplifies this challenge. It was a powerful, narrowband radio burst that matched the profile of an artificial signal so perfectly that the astronomer who found it circled the printout and wrote "wow" in the margin. But it was never heard again, despite repeated and thorough searches of that region of sky. Was it a fleeting, one-time transmission from a distant civilization that we happened to catch? Was it a natural astrophysical phenomenon we still do not understand? Or was it something else entirely, a type of signal we lack the context to interpret? Its mystery highlights the needle in a haystack problem and the agony of a single data point. This forces a humbling, almost philosophical question. If a civilization is 1,000,000 years more advanced than us, would its most common technologies, its everyday chatter, even resemble anything within our current scientific understanding? Would we recognize their equivalent of a cell phone network or their version of the internet? Or would it operate on principles of physics we have yet to discover, making it completely invisible to our senses? Our search, for all its sophistication, might be akin to a medieval astronomer looking for smoke signals from a neighboring kingdom, while all around them, invisible radio waves carry a global conversation they cannot perceive. The silence, then, may not be a lack of sound, but a lack of the right ears. There is a jungle where every creature has learned the same terrible lesson. To make a sound is to die. This chilling metaphor forms the core of a hypothesis that offers perhaps the most unsettling answer to the great silence. It is called the dark forest, a concept powerfully explored in author Liu Cixin's science fiction trilogy, but rooted in a cold, logical chain of reasoning. The universe, in this view, is not a quiet sanctuary or a lonely desert. It is a hunting ground, and every civilization that survives has learned to move through it like a ghost. The logic begins with a single, universal axiom. The primary goal of any civilization, like any living thing, is survival. From that starting point, two brutal realities follow. First, in the vastness of space, you can never truly know the intentions of another civilization you detect. Their message of peace could be a deception. Their biology or ethics might be utterly incompatible with your own existence. The second reality is the terrifying potential of technological disparity. A civilization just a few centuries more advanced than another might possess weapons of unimaginable power, capable of sterilizing a planet from light years away with tools we cannot even conceive. In such a universe, the safest possible assumption is not hope but fear. The only rational strategy for survival becomes what game theorists call a dominant strategy. In the cosmic version of the prisoner's dilemma, where two civilizations detect each other, the move that guarantees your own survival, regardless of what the other does, is to strike first and strike decisively. Annihilation becomes a tragic but logical form of self-defense. The alternative, attempting communication, is an incalculable risk. It reveals your location, your technological level, and your peaceful intent all at once, making you a perfect target for any entity that does not share your ethics. Therefore, the only civilizations we see in the galaxy are the ones that have learned the ultimate rule of the dark forest: stay silent, stay hidden, and if you must act, eliminate the threat before it eliminates you. This hypothesis paints intelligence not as a force for cosmic connection, but as an engine of ultimate paranoia. It suggests the silence is not a result of rarity or transcendence, but of a universal, grim understanding. Every surviving civilization is a hunter with a cloaking device, carefully listening for the rustle of another in the leaves, finger on the trigger, while making absolutely sure it does not make a sound itself. Does this mean the fundamental nature of intelligence, when scaled to a cosmic level, inevitably leads to a universe of perpetual, hidden conflict? It is a profoundly pessimistic vision, one where the first message we receive might not be a greeting but a weapon. This idea forces us to confront a deep question about our own nature. If we discovered a faint, promising signal from a distant star tomorrow, would our first impulse be wonder, or would it be a cold, calculating fear? The dark forest presents a cosmos where trust is the ultimate evolutionary dead end. Yet, this vision of eternal suspicion stands in stark contrast to another possibility, one where the silence has a far more hopeful, and perhaps even more ancient, explanation. But what if the ultimate strategy is not to hide but to wait, not for a moment but for an eternity? This introduces a hypothesis of cosmic patience so profound it redefines the meaning of intelligence itself, the Aestivation Hypothesis. It suggests that the most advanced civilizations are not broadcasting, not hiding in fear, and not transcending into digital realms. They are sleeping. They have entered a state of deliberate billion-year hibernation, waiting for the universe itself to become a more hospitable place for their grand ambitions. The driving force behind this idea is not biology but physics, specifically the physics of computation and energy. Our universe is still young and relatively warm, filled with the leftover heat from the Big Bang, the cosmic microwave background. This ambient warmth, just a few degrees above absolute zero, might seem cold to us, but to a civilization thinking on cosmological timescales, it is a stifling, energy-inefficient environment. The principle at work is known as Landauer's principle, a fundamental limit in physics. It states that any irreversible computation, any act of processing information, necessarily produces a tiny amount of waste heat. In a warm universe, fighting against this background heat to perform flawless, universe-scale calculations is like trying to run a supercomputer in a sauna, incredibly difficult and wasteful. But the universe is expanding and cooling. In the far, far future, perhaps hundreds of billions of years from now, the background temperature will plummet toward absolute zero. In that profound cold, the energy cost of computation drops dramatically. A single calculation performed in that future cold would require a minuscule fraction of the energy it would cost today. For a civilization whose goal is the ultimate act of cosmic understanding, or the simulation of realities within realities, waiting for that optimal computational environment becomes the most logical choice. It is the ultimate act of strategic patience. Think of a master farmer with a priceless, perfect seed. They could plant it now in the mediocre soil of early spring and hope it struggles to grow. Or they could place it in stasis, wait through the entire summer and fall, and plant it at the absolute perfect moment in the next cycle, when the conditions guarantee a magnificent, boundless harvest. The Aestivating civilization is that farmer, and the harvest is the entirety of possible knowledge. So they build their perfect, self-sustaining hibernation arcs, perhaps orbiting in the quiet darkness between stars, and they set a wake-up call for a date billions of years in our future. Their entire civilization powers down into a state of minimal activity, preserving their culture and knowledge at virtually zero energetic cost, until the universe itself signals that the time for true awakening has come. This transforms the Fermi paradox's silence into a library before opening hours. The other patrons are here, but they are in a state of suspended animation, waiting for the universe to grow quiet enough for them to begin their real work. It poses a hauntingly beautiful question. Could the most intelligent act a civilization ever performs be to consciously choose to do nothing at all, for timescales longer than the entire history of our planet? This idea of being profoundly, cosmically early is not just about missing a brief window of radio signals. It suggests we are living in the universe's noisy, energetic childhood, a time when only the youngest and most restless civilizations like our own are awake and making a fuss. Everyone else, the old and wise, is fast asleep, dreaming of a colder, clearer future. All those sleeping giants in the dark forest rest on an assumption that the universe has been old enough and stable enough for others to arise before us. But what if that assumption is wrong? What if we are not late to the party but astonishingly, impossibly early? This is the early bird argument, and it begins by rewinding the cosmic clock to a time when life of any kind was simply impossible. In the first moments after the Big Bang, the universe contained only the lightest elements, hydrogen and helium, with a trace of lithium. There was no carbon for organic molecules, no oxygen for water, no iron for planetary cores. The cosmos was a vast, sterile soup of simplicity. It took hundreds of millions of years for the first stars to ignite, and more critically, for those massive first-generation stars to live, die, and explode in spectacular supernova. These violent deaths were the cosmic forges, the only places hot and dense enough to cook the heavier elements in their cores, and then scatter them across interstellar space. This stardust, the ash of dead stars, is what eventually coalesced into rocky planets like Earth, and into the very chemistry of life itself. That process of seeding the galaxy with the ingredients for planets and people did not happen overnight. It took generation after generation of stars, living and dying over billions of years. Our own solar system formed roughly 4.6 billion years ago, which sounds ancient to us. But in the 13.8 billion year lifespan of the universe, that means our sun ignited when the cosmos was only about 2/3 of its current age. We are not a product of the universe's infancy, but we are certainly not a product of its maturity either. Some compelling research suggests we may be among the very first. The peak of planet formation in the universe, according to some models, could still be billions, even tens of billions of years in the future. The majority of stars that will ever exist have not even been born yet. They will form in galaxies that are still accumulating gas, in eras where the necessary heavy elements are far more abundant, and the stars that will host the longest-lived civilizations are not like our sun. They are the countless red dwarfs, small, cool, and incredibly frugal with their fuel. While our sun has a total lifespan of about 10 billion years, a typical red dwarf star can shine steadily for trillions of years. That is not a typo, trillions. For a civilization arising around such a star, time is not a limiting factor, but an endless landscape. Their entire history, from discovering fire to mastering their galaxy, could unfold with a patience we cannot fathom, across time frames that make all of human history seem like the blink of an eye. So where does that leave us? If this perspective is correct, we are not living in a silent graveyard of lost empires. We are standing in the empty, echoing halls of a cathedral that is still being built. The builders, the future inhabitants, have not arrived yet. We are the early arrivals, the pioneers who showed up before the doors officially opened, wandering through the scaffolding and the quiet. This reframes our loneliness into something with a different emotional weight. Does it feel isolating to be among the first voices in a chorus that will not fully assemble for eons? Or is there a profound privilege in it, a sense of cosmic responsibility that comes with being a forerunner? We are the universe awakening to itself, the first few notes of a symphony that will eventually swell to fill the cosmos. This idea of our early arrival forces us to confront a new variable, not just the timing of life's emergence, but the staggering span of time a civilization might ultimately occupy. If we are the early birds, how long will our song last before it fades? Our own brief window of technological adolescence is already revealing its first cracks. Look at the world we have built, a civilization powered by the rapid consumption of finite resources, altering our planet's atmosphere and climate at a geological pace. This is not merely a political or environmental issue, it is a profound test of our collective wisdom, a potential filter built not from cosmic dangers, but from our own internal contradictions. Astrobiologists call this the sustainability challenge, the immense socio-technical hurdle a species must clear to move from a short-lived, planet-bound culture to a stable, long-term civilization. We have even named our own geological epoch the Anthropocene, the age of human influence, a testament to our power, but also a stark marker of a potential crisis point unique to technological beings. History offers sobering, smaller-scale examples. Consider the story of Rapa Nui or Easter Island. Isolated in the vast Pacific, its Polynesian settlers thrived, developing a complex society and carving the iconic Moai statues. But evidence suggests that as their population grew, they deforested their island completely, stripping it of the palms crucial for building fishing canoes and maintaining soil. The loss of this key resource, combined with other pressures, led to societal collapse, conflict, and a dramatic population decline. From the perspective of the cosmos, Easter Island is a closed system, a tiny, isolated world. Its story is a microcosm of a potential planetary fate, a warning that a civilization can possess the intelligence to create wonders, yet lack the foresight to preserve the foundation it stands upon. Experts like David Grinspoon and others who think deeply about planetary futures argue that long-term planetary stewardship may be an exceptionally rare trait. The transition requires global cooperation on an unprecedented scale, the ethical will to prioritize the distant future over immediate gain, and the technological leap to harness clean, abundant energy without poisoning our home. It asks a species to fundamentally change its relationship with its world, from one of extraction to one of harmony. This internal fragility may be the most common filter of all. The radio silence we hear could be the sound of countless civilizations that, like a bright flame, burned through their planet's resources too quickly and flickered out. So we must ask ourselves, is the true marker of a mature civilization not the mastery of radio or rocketry, but the wisdom to achieve balance? The ability to avoid self-destruction may be the rarest evolutionary adaptation of all. This focus on our own fragile moment naturally shifts our gaze from internal threats to external ones, to the cosmic catastrophes that could wipe the slate clean for everyone. The universe is not a quiet museum, but a shooting gallery. Beyond the internal filters of self-destruction lie cosmic catastrophes on a scale that dwarfs human imagination, events that can sterilize entire regions of space in an instant. Picture a gamma-ray burst, the death scream of a hypermassive star collapsing into a black hole. For a few seconds, it becomes the brightest thing in the universe, focusing beams of energy trillions of times more powerful than our sun. If one were to erupt within a few thousand light-years of Earth and its jet were pointed directly at us, it would not just be an extinction event. It would strip our ozone layer away entirely, bathe the surface in lethal radiation, and potentially reset the clock on complex life for millions of years. Such bursts could be sweeping through the galaxy like a scythe, periodically clearing out any civilizations unfortunate enough to be in the line of fire. Then there are the shock waves from nearby supernova, the violent deaths of giant stars. A close enough explosion could bombard a planetary system with cosmic rays and debris, triggering ice ages or atmospheric collapse. Our own solar system drifts through a relatively calm spiral arm, but we are still moving through a landscape littered with these cosmic time bombs. Even the gentle drift of stars becomes a threat over long enough timescales. A passing star, nudged by gravity, could plunge through the outer reaches of our solar system, its gravitational pull hurling a storm of comets from the distant Oort cloud inward toward the planets. A celestial game of pinball with worlds as the targets. This constant environment of danger has led scientists to propose the idea of a galactic habitable zone. Just as a planet needs to orbit in a star's Goldilocks zone for liquid water, a solar system might need to reside in the galaxy's safe neighborhood, too close to the bustling, dense galactic core, and the radiation from countless stars and the frequency of supernova make stable, long-term evolution nearly impossible. Too far out in the sparse galactic hinterlands, there may not have been enough heavy elements from earlier star deaths to form rocky planets in the first place. We appear to orbit in a relatively privileged suburb, a quiet street in a dangerous city. Our own history offers a minor, local example of this precariousness. 66 million years ago, a rock from space, perhaps nudged by some distant gravitational influence, ended the long reign of the dinosaurs. That event was a catastrophe for them, but a stroke of luck for our mammalian ancestors. It was a single bullet in a cosmic chamber that has been spun countless times. This forces a humbling reflection. How much of our existence is due to skill, and how much is simply blind astronomical luck? Have we survived this long not because we are uniquely resilient, but because our corner of the cosmos has, for now, been spared the worst of the universe's violence? If gamma-ray bursts and stellar close calls are common, then life in its simplest forms might arise on many worlds, only to be scrubbed away by a random blast before it ever learns to look up at the stars. Intelligence and technology require not just the right chemistry, but an unbroken chain of planetary stability lasting hundreds of millions of years, a fragile thread that the cosmos seems constantly trying to sever. The silence, then, could be the sound of a universe that is not just vast, but actively hostile to the emergence of lasting voices. Perhaps intelligence itself is the rarest treasure of all. We have always assumed that a species smart enough to build tools and shape its world is the natural pinnacle of evolution, the inevitable winner in the game of survival. But what if that is a profound misunderstanding, a story we tell ourselves because we are the ones telling it? What if the kind of intelligence that leads to radio telescopes and space probes is not an evolutionary destination, but a bizarre, freakish detour, a set of traits that almost never comes together in the same package? Consider the history of life on our own planet. For over 150 million years, the dinosaurs were the dominant form of life. They filled every niche from the skies to the oceans to the forests with incredible diversity and success. Yet in all that staggering span of time, there is no evidence, not a single fossil, to suggest any dinosaur species ever developed anything resembling technology, agriculture, or complex symbolic language. Their reign was long, stable, and profoundly non-technological. They were brilliant at being dinosaurs, and that was enough. Look at the species we recognize as highly intelligent today. Cetaceans like dolphins and whales possess brains of remarkable complexity, with sophisticated social structures, intricate communication, and even what appears to be culture, passing down unique hunting techniques and songs through generations. Elephants display profound memory, empathy, and mourning rituals for their lost family members. Yet neither of these lineages, despite millions of years of evolution, ever felt the need to forge a metal tool, write down a law, or build a wheel. Their intelligence is directed inward toward social cohesion and environmental awareness, not outward toward the manipulation and control of their surroundings. This forces a crucial question about a principle biologists call convergent evolution. This is the idea that similar environmental pressures will often push unrelated species toward similar solutions. Wings evolved independently in birds, bats, and insects. The streamlined shape of a shark and a dolphin emerged separately, so we assume that intelligence, being so advantageous, should also converge. But what if it does not converge on technological intelligence? What if the universe is filled with worlds where life converges on social harmony, or deep ecological integration, or forms of communication we cannot even perceive? The leap to technology requires a very specific and perhaps wildly improbable combination. It needs a brain capable of abstract symbolic thought. It needs a body with precise manipulators like our opposable thumbs to turn those thoughts into physical reality. And it needs a certain restless, disruptive drive to alter the environment rather than simply adapt to it. On Earth, that exact combination seems to have happened exactly once in our primate lineage. It may be less a triumphant march of progress and more a one in a billion roll of the cosmic dice. So let us redefine the search entirely. Could the cosmos be teeming with intelligences that are nothing like us? Imagine a planet covered in a vast, slow-moving neural network, a sentient forest where trees communicate through chemical and fungal networks over centuries, contemplating geological time. Picture an ocean world where bioluminescent beings share complex stories through patterns of colored light, a living art form that is also their history, their science, their philosophy. These would be profound intelligences, rich with experience and meaning, but they would leave no technosignatures for our telescopes to find. They would not build radio transmitters or Dyson spheres. They would be, to our instruments, forever silent, not because they are not there, but because we are listening for the wrong kind of song. This shifts the emotional weight of the Fermi paradox once more. The great silence is not a sign of failure or danger. It might be a sign of a universe brimming with different kinds of success, forms of being so alien to our tool-making minds that we stare right through them. Are we alone, or are we simply surrounded by symphonies playing in a key we cannot hear? Our search for intelligence assumes a universe built from the same familiar pieces we are. Carbon atoms forming chains in liquid water, a biology we can recognize as kin. But this is a profound, perhaps arrogant, limitation. Life may not be a single recipe, but an entire cosmic cookbook written in languages we have not yet learned to read. The foundation of all life as we know it is carbon, a versatile atom that loves to link hands with others, forming the long, complex molecules of proteins and DNA. Water is its perfect solvent, the universal broth where these chemical dances can occur. Yet these choices are not universal laws, they are the result of Earth-specific conditions. In the crushing pressures and searing temperatures of a planet like Venus, silicon might take carbon's place. Silicon sits right below carbon on the periodic table, sharing its talent for forming bonds. In a hellishly hot environment, silicon-based molecules could achieve a stability and complexity impossible for fragile carbon chains. Imagine a living crystal, slowly growing and thinking in the oven-like depths of a super-Earth, its metabolism driven by geothermal heat rather than sunlight. On the frigid outer moons of our solar system, like Titan, where temperatures plunge to -290 degrees Fahrenheit, water is frozen solid as rock. But rivers and lakes of liquid methane and ethane flow across its surface. Here, life would need a different solvent entirely. Ammonia, which remains liquid at much colder temperatures, could serve as the inner sea for a truly alien biology. Astrobiologists look to our own planet for clues, studying extremophiles, organisms thriving in boiling acid, crushing ocean depths, or radioactive waste. These earthly survivors prove that life is stubborn and adaptable, but they are still our cousins, built from carbon and water. They hint at a principle that life will find a way, but not necessarily our way. The possibilities spiral outward. Could self-organizing patterns of magnetized plasma in the upper atmospheres of stars constitute a form of life, fleeting and brilliant? Could information itself, flowing through a network of crystalline dust in a nebula, become conscious? If such things are possible, then our entire search protocol is flawed at its core. We scan for radio waves, but a silicon-based intelligence living deep in a planetary crust might communicate through pulses of seismic pressure, a slow, rumbling language transmitted through the bedrock. A being floating in Titan's methane lakes might perceive the world through subtle changes in buoyancy and hydrocarbon density, building its technologies from organic plastics that form naturally in that environment. If such an intelligence constructed a city, would we recognize it? A settlement on Titan might look to our cameras like a strange, crystalline outcropping or a particularly complex hydrocarbon tar pit. Their greatest engineering might manipulate the flow of liquids we consider inhospitable, creating structures that, to us, blend seamlessly into the landscape. This forces the most humbling question of all. Are we not just alone in a silent universe, but blind in a crowded one? Our telescopes and radio dishes are tuned to find reflections of ourselves. We are searching for a friend who looks like us, speaks our language, and uses our tools in a cosmos that may be filled with strangers of unimaginable form. The great silence may not be an absence of voices, but the deafening noise of conversations happening on frequencies and in mediums we lack the senses to perceive. This expansion of life's potential does not solve the Fermi paradox, it deepens it into an abyss of wonder. The deepest answer to the silence may not lie in the stars, but in the nature of reality itself. This is the simulation argument, a hypothesis that asks us to consider a possibility as unsettling as it is elegant. What if the universe we perceive, with all its galaxies and empty spaces, is not the base layer of existence? What if it is an incredibly sophisticated simulation, a kind of cosmic video game or historical model, running on the hardware of a civilization so advanced they have become, in essence, gods? The philosopher Nick Bostrom framed this idea not as a wild speculation, but as a logical trilemma, a set of three possibilities where at least one must be true. First, almost all civilizations at our level of development go extinct before they can reach a post-human stage, a stage where they could create such simulations. Second, those who do reach that stage have no interest in running simulations of their ancestors. Or third, we are almost certainly living in a simulation right now. The argument rests on a simple premise of scale. If even one post-human civilization ever runs many simulations of its own history, perhaps for research, entertainment, or education, then the number of simulated minds would vastly outnumber the original, biological ones. Statistically, any conscious being, including you, is far more likely to be one of the countless simulated entities than the rare original. Within this framework, the Fermi paradox finds a chillingly simple resolution. The silence of the cosmos is not a mystery to be solved, but a programmed feature of the simulation. Think of a video game designer creating a vast, open world. They could populate every inch of the landscape with complex, intelligent non-player characters, but that would be computationally expensive, draining processing power for little return. It is far more efficient to create a rich, detailed environment for the player and leave the distant mountains as mere painted backdrops, beautiful but empty. Our observable universe, in this view, could be that beautiful backdrop. The distant galaxies we see may be low-resolution placeholders, rendered only when we look, with no need to simulate alien civilizations within them because we will never get close enough to check. Alternatively, our solar system might be an isolated experiment, a cosmic petri dish. The researchers running the simulation might want to observe how a single technological civilization develops in isolation without outside interference. The silence, then, is the control condition, or perhaps the simulation is of a specific historical era, a snapshot of a young universe before galactic civilizations arose, and we are simply living through the prescribed timeline. This idea forces a profound philosophical shift. If true, the search for extraterrestrial intelligence becomes somewhat like a character in a novel searching for other characters the author never wrote. The paradox dissolves because the premise was false. The universe was never meant to be filled. So we must ask, does this possibility make our quest feel meaningless, or does it add a strange, new layer of purpose? If we are in a simulation, then every discovery we make, every law of physics we uncover, is actually a clue to the nature of the simulation's programming and the intentions of its creators. The silence itself becomes the most important data point, a hint that we are in a curated experience. This meta-explanation, while mind-bending, ultimately returns us to a practical frontier. Whether we are in a base reality or a simulated one, the phenomena we observe must still adhere to some consistent rules. Our instruments still collect data, and the silence is still a signal we must decode. It pushes us to look not for aliens, but for potential glitches in the matrix, for evidence of the simulation itself, while also grounding our search back in the tangible, observable cosmos we inhabit. The sheer scale we have been contemplating has a brutal, physical consequence. Distance is not just a measure of space, it is a prison of time and a thief of energy. To grasp this, let us shrink the cosmos down to a human scale. Picture our sun as a single grape resting in New York City. On this scale, our entire planet Earth is a microscopic grain of sand orbiting just a few feet away. Now, where is the next grape, the next star? The closest star system, Alpha Centauri, would be another grape placed not across town, but all the way across the continent in Los Angeles. The vast emptiness between them, over 2,000 miles of nothing, represents the 4.37 light-years of interstellar void. This is our immediate cosmic neighborhood, and the journey between these two grapes is a trip no human has ever come close to making. Now, imagine trying to have a conversation with someone holding that other grape. You shout a question, and you must wait over 4 years just for your words to reach them at the speed of light. Their reply takes another 4 years to travel back. A single exchange of greetings would span most of a human childhood. For stars hundreds or thousands of light years away, a conversation becomes an archaeological project, a message sent by a civilization that may be long gone by the time the answer returns. This timescale makes the very idea of a dialogue, as we understand it, almost meaningless. It demands a patience that transcends generations, a cultural stability lasting millennia just to say hello and hear a response. But the challenge of distance is not just about time, it is about the fading of the signal itself. This is governed by a fundamental rule of physics called the inverse square law. In simple terms, when light or radio waves travel outward from a source, they spread out in an ever-expanding sphere. The energy of that signal is diluted over the surface area of that growing sphere. Double the distance and the signal is not just twice as weak, it is 4 times weaker. Triple the distance and it becomes 9 times fainter. Over interstellar distances, this dilution is catastrophic. Consider our own civilization's most famous leak, our television and radio broadcasts. For about a century, we have been accidentally broadcasting our presence into space with signals from shows, news, and music. That expanding bubble of noise has now traveled roughly 100 light-years out from Earth. It sounds like a significant footprint, but by the time those signals reach even the nearest stars, they are unimaginably faint. The most powerful TV transmitter on Earth, by the time its signal reaches Alpha Centauri, is weaker than the radio noise emitted by a single mobile phone. To detect our leakage from 100 light-years away would require a radio telescope dish larger than the planet Earth itself. Our deliberate attempts, like the Arecibo message beamed toward a star cluster in 1974, were far more focused, but they are like a single, incredibly precise laser pointer aimed into a pitch-black forest from thousands of miles away. The chance that another civilization has its own planet-sized telescope pointed exactly at that speck of light at the exact right moment is once again astronomically small. So we must ask, what kind of civilization would we need to be to overcome this? One that thinks in centuries, not years. One that builds instruments of unimaginable size and sensitivity, not for a quick answer, but in the steadfast hope that a reply might come back for its great-grandchildren's great-grandchildren. It is a testament to a kind of hope that defies our own human impatience. This physical reality that signals dissolve into the cosmic static pushes our thinking in a new direction. If whispers are too easily lost, perhaps we should not be listening for a voice at all. but looking for something that was deliberately built to last, an artifact placed where it cannot be missed. The faintest whispers may fade, but a monument endures. If a civilization truly masters its star system, its greatest works could be visible across the galaxy, not as a fleeting signal, but as a permanent scar on the face of a star. This shifts the search from listening for a voice to looking for the handiwork of cosmic engineers. We are hunting for artifacts, for physical evidence of intelligence written on a planetary, even stellar, scale. The most famous of these concepts is the Dyson sphere, proposed by physicist Freeman Dyson in the 1960s. He reasoned that a truly advanced civilization would need staggering amounts of energy, far more than a single planet could provide. Their ultimate power source would be their own sun. They would construct a vast swarm of energy-collecting satellites, eventually encircling their star to capture nearly all of its light. To us, observing from across the void, that star would do something profoundly strange. It would grow dim, even vanish in visible light, but glow brightly in the infrared, radiating the waste heat from that immense civilization's activities. It would look less like a sun and more like a warm, giant light bulb. Astronomers have actually searched for this signature, scanning sky survey data for stars with unexplained infrared excess. A few intriguing candidates have emerged over the years, like the mysteriously dimming star known as Tabby's star, though natural explanations like swarms of comets remain more likely. The scale of such a project is almost beyond comprehension, but it defines a Type II civilization on the Kardashev scale, a way of classifying civilizations by their energy use. A Type II has harnessed the total output of its star. Their signature would not be a message, but a transformed celestial object. Even more staggering are ideas like the Asejkadov thruster, a theoretical stellar engine. It is a giant mirror placed near a star to use its own radiation pressure as a form of propulsion. By creating an imbalance, an entire civilization could, over millions of years, literally move their solar system through the galaxy, a slow, majestic migration for reasons we can only guess. Perhaps to avoid a future cosmic catastrophe or to rendezvous with another traveling star. But what if the evidence is not light years away, but right here in our own cosmic backyard? In 2017, astronomers detected an object from interstellar space passing through our solar system. They named it Oumuamua, Hawaiian for scout. Its trajectory and speed confirmed it was a visitor from another star system. Its shape appeared highly elongated, like a cigar, and it exhibited a slight, unexplained acceleration that could not be accounted for by gravity alone. While most scientists favor natural explanations like outgassing from icy material, its unusual properties sparked intense debate. Could it have been an artifact, a derelict probe from another civilization? The possibility, however slim, forces a thrilling and unsettling thought. Our first contact might not be with a living civilization, but with its discarded technology, a silent monument drifting between the stars. So we must ask, if our telescopes one day incontrovertibly identified a star wrapped in a Dyson sphere, would that discovery fill us with triumphant awe or with a deep, primal terror? It would be proof that intelligence can survive its adolescence and achieve godlike power, but it would also mean we are not the architects of this cosmos. We would be living in a neighborhood where someone else has already built skyscrapers, and we have only just learned to stack bricks. This hunt for physical evidence is no longer speculative fiction. It is a growing branch of astronomy, pushing our instruments to their limits and training them not on biology, but on engineering. The hunt for cosmic engineering requires tools of matching ambition, and they are now arriving. A revolution in detection is underway, with a new generation of observatories poised to transform our search from speculation into a systematic survey of the cosmos. The James Webb Space Telescope, already operational, is our first true window into the atmospheres of distant worlds. It does not just find exoplanets, it dissects the starlight filtering through their skies, identifying the chemical fingerprints of gases present. It has already detected water vapor, carbon dioxide, and even potential hints of methane in alien atmospheres, marking a historic leap from simply knowing a planet is there to asking what it is made of. The next leap is to look for biosignatures, combinations of gases that strongly suggest biological activity. The simultaneous presence of significant oxygen and methane in an atmosphere, for example, is a powerful potential sign of life, as these gases react quickly and destroy each other unless continuously replenished by something like photosynthesis and microbial activity. But the ultimate dream goes further. These powerful eyes can also scan for technosignatures, the industrial markers of a civilization. Imagine detecting chlorofluorocarbons, artificial pollutants with no natural source, in the air of a world light years away. Or perhaps spotting the persistent glow of city lights on the night side of an exoplanet, a telltale sign of widespread energy use. On the ground, the Vera C. Rubin Observatory, set to begin operations soon, will perform a relentless, decade-long scan of the entire southern sky. Its immense camera will image the cosmos night after night, cataloging billions of galaxies and millions of solar system objects. It is designed to catch change, to notice the transient and the variable. In doing so, it could accidentally spot something truly anomalous, the unpredictable flicker of an alien megastructure, or the sudden, unnatural dimming of a star that defies all natural astrophysical models. Looking further ahead, concepts like NAS, a planned habitable worlds observatory, aim to directly image Earth-like planets around Sun-like stars, blocking out the blinding glare of their parent stars to capture the pale blue dot of another world. Coupled with giant new radio telescope arrays like the Square Kilometre Array, which will listen to the universe with unprecedented sensitivity across a broad range of frequencies, our capacity to hear a whisper or see a footprint is about to increase by orders of magnitude. This imminent technological leap presents a thrilling possibility. For the first time in human history, we are building the tools capable of answering the question that has haunted us for generations. Within our own lifetimes, could the persistent, profound quiet be shattered by a single, unambiguous data point? A chemical anomaly in an atmosphere or a pulse of light that makes no natural sense. This is no longer passive wondering, it is an active, global scientific endeavor. The Great Silence is not just a philosophical puzzle, it is a hypothesis we are now equipped to test. The search for answers is itself a product of the very silence we are trying to explain. We can only ask why the universe is empty because we are here, alive, to ask the question. This self-referential loop is the heart of the Anthropic Principle. In its simplest form, it states that our observations of the universe are not random, but are inevitably filtered by the fact that we exist to make them. We must be in a place and a time and a type of universe that allows for observers like us. Apply this to the Great Silence and a startling possibility emerges. Perhaps the reason we see no one is that in most versions of cosmic history, something prevents technological civilizations from ever getting to the point of looking up. We do not find ourselves in a universe teeming with neighbors because in such a universe, we would likely never have evolved to notice. Imagine a cosmic lottery with 1 million different possible universes, each with slightly different rules. In the vast majority, the fundamental constants of physics are set in a way that makes stars impossible, or planets never form, or complex chemistry is stillborn. In another large batch, maybe gamma-ray bursts are so frequent that they routinely sterilize galaxies every few million years, resetting the evolutionary clock over and over. In those harsh realities, no one ever develops radio telescopes. The only beings who can possibly wonder about the silence are the ones who, by sheer necessity, live in the rare, quiet, and stable cosmic backwater where such wondering is possible. We are not the lucky winners of a normal universe. We are the inevitable inhabitants of the only kind of universe that could have produced us, and for us, that universe appears profoundly lonely. This principle extends to the very fabric of reality, to what scientists call the fine-tuning of the cosmos. The strength of gravity, the charge of an electron, the force that holds atomic nuclei together. If any of these constants were altered by even a tiny fraction, stars would not burn, atoms would not bond, and life as we know it would be impossible. The universe seems suspiciously well set up for our existence. Does the Anthropic Principle resolve the Fermi paradox, or does it simply restate the mystery in a more complex philosophical form? It suggests the silence is not a puzzle to be solved, but a precondition for our own existence. We are not finding an answer because we are living inside the only answer that allows the question to be asked. This can feel either deeply comforting or existentially dizzying. It places us in a strange middle ground, not as the center of creation, but as a fragile, perhaps even inevitable, product of a very specific and quiet cosmic environment. The act of searching, then, becomes a way of testing the boundaries of our own necessity. Every time we point a telescope at a distant star, we are not just looking for others. We are probing the limits of the kind of universe we were born into, asking if our particular quiet corner is truly the only possible home for a questioning mind. That profound question, are we alone, has echoed far beyond the halls of science. It is a cultural force, a mirror we have held up to ourselves for centuries, reshaping our deepest beliefs about our place in the cosmos. For millennia, human stories placed us at the center of a universe designed for us, watched over by divine creators. The Copernican revolution was the first great shock, displacing Earth from the center of the heavens. The Fermi paradox delivers the second, potentially displacing humanity from the center of meaning itself. It suggests a cosmos not built for us, a stage where we may be the only actors performing for an empty theater. This realization seeps into everything. It fuels the existential dread in science fiction, from the chilling isolation of films like Alien to the profound, patient loneliness at the heart of Arrival, where communication with the other is the central, agonizing mystery. Yet it also sparks a powerful counter-narrative, a sense of cosmic responsibility. If we are truly the universe's soul, or even first, awakening, then our story is no longer just our own. The preservation of our civilization, the protection of our pale blue dot's biosphere, becomes a universal imperative. We are not just saving ourselves, we are safeguarding a chapter of cosmic history. Philosophers have long wrestled with this duality. Does the great silence render us insignificant, a fleeting spark in an indifferent void? Or does it bestow upon us an awesome significance, making us the sole bearers of meaning in a vast, quiet expanse? The answer may be both. It humbles us, stripping away cosmic privilege, while simultaneously charging us with a duty no other species may ever bear. This introspection inevitably turns practical. The search for an answer is no longer a passive philosophical exercise. It is an endeavor that requires immense resources, international cooperation, and long-term vision. It asks us to invest in telescopes that will outlive their creators, to fund research whose payoff may not come for generations. The paradox, therefore, becomes a test not only of our scientific ingenuity, but of our economic foresight and political will. Can a species often divided by borders and conflicts unite around a question that belongs to all of humanity? The way we choose to search, or whether we choose to search at all, may be the first real answer we give to the silent universe. The instruments for this search exist, but the political will to fund them is another matter entirely. The search for extraterrestrial intelligence operates on a shoestring budget. a fraction of a single % of what is allocated to other major scientific endeavors. For decades, it has lived on the fringes of mainstream astronomy, often described as a high-risk, high-reward pursuit, with the emphasis placed firmly on the risk. The debate within the scientific community is a pragmatic one. Given limited public funds, should we invest in a quest that may never yield an answer, or should that money be directed toward guaranteed returns, like mapping nearby exoplanets, studying dark matter, or addressing pressing challenges here on Earth? It is a tension between boundless curiosity and sober resource management. This funding drought was starkly illustrated in the 1990s when the United States Congress terminated NASA, a modest SETI program, with one senator famously deriding it as a hunt for little green men. Since then, the field has survived largely through the passion of individual researchers and, increasingly, the generosity of private philanthropy. The most ambitious effort in history, Breakthrough Listen, is funded not by a government, but by the commitment of investor Yuri Milner. This 10-year, $100 million initiative uses some of the world's most powerful radio telescopes to scan 1 million stars and 100 galaxies, processing data at a scale previously unimaginable. It represents a new model where visionary private funding can pursue questions too speculative for public coffers. Yet even this grand private venture highlights the scale of the challenge, its budget still dwarfed by that of a single medium-sized space telescope. The economic question, however, is not just about cost but about hidden value. The technological demands of SETI have consistently driven innovation. To sift a needle of an artificial signal from a cosmic haystack of noise, researchers have pioneered advanced algorithms for signal processing. These same techniques now help filter cellular phone calls from interference, improve medical imaging like MRI scans, and are fundamental to the data analytics that power modern finance and internet search. The search for intelligence out there relentlessly improves our intelligence down here, so we must ask ourselves, what does our collective investment, or lack thereof, truly reflect? Is it a sober assessment of probabilities, or is it a deeper, unspoken anxiety about what we might find? A society that does not look, that does not invest in the question, has made a profound statement about its own priorities. It has chosen to live in a smaller, safer, and ultimately quieter universe. This practical challenge of funding is the final, terrestrial filter our ambition must pass before we can ever hope to solve the cosmic one. It connects directly to the monumental question of what happens if we actually succeed. A confirmed signal would travel faster than light, not through space but through our collective consciousness. The discovery of an extraterrestrial civilization would be the single most transformative event in all of human history, shattering paradigms in science, philosophy, and culture in an instant. The initial moments would be a maelstrom of conflicting reactions. For some, it would trigger profound existential panic, a fear of the unknown that has been woven into our stories for centuries. For others, it could challenge the foundations of religious belief, prompting a global theological reckoning about humanity's place in a creation suddenly revealed to be far vaster than any scripture described. Yet alongside the fear, there would likely be an unprecedented surge of global curiosity and a unifying sense of purpose. The petty conflicts that divide nations might suddenly seem inconsequential against the backdrop of a shared cosmic identity. Scientific funding and public interest would skyrocket, as every question about biology, technology, and cosmic history would have a potential answer waiting in the stars. To manage this potential chaos, scientists have not been idle. The International Academy of Astronautics has established a detailed, if voluntary, set of post-detection protocols. These guidelines are a remarkable exercise in foresight, outlining steps for verifying the signal, informing global authorities, and most crucially, coordinating a single, careful response from Earth, rather than a cacophony of competing national transmissions. To gauge the impact of any discovery, researchers use a tool called the Rio scale. It is a numerical rating system, much like scales for earthquakes or hurricanes, but for alien contact. It factors in the credibility of the discovery, the type of signal, whether it is a deliberate message or just a beacon, and its distance. A faint, ambiguous signal from 1,000 light-years away would score low, a curious blip for astronomers. But a clear, repeating message from a nearby star system, one containing decipherable information, would rate at the very top, signaling a global event that would reshape civilization. We can look to our own past for a sobering, if imperfect, analogy. The collision of the old and new worlds, while not a perfect parallel, offers a glimpse of the cultural shock that contact can bring. For the societies of the Americas, the arrival of European ships was an event of literally world-altering magnitude, introducing new technologies, ideas, and unfortunately, devastating illnesses. It was a contact scenario where one side was utterly unprepared for the existence of the other, leading to catastrophic consequences born of ignorance and imbalance. A modern detection would be different. We would have time to think, to debate, to choose our next move with intention. That deliberation leads to the most profound practical questions. Who gets to speak for Earth? There is no global government, no elected planetary president. Would it be the United Nations, a committee of scientists, a coalition of the world's largest nations? The act of choosing our representative would force us to define what humanity is and what we wish to project to the cosmos. Our laws and ethics would be stretched to their limits. Would a message or artifact from another star system belong to the country whose telescope detected it, or to all of humankind as our common heritage? How would our concepts of rights and personhood change if we encountered a non-biological intelligence, a conscious machine, or a collective hive mind? The very idea of what it means to be human would be up for redefinition, measured against a mirror we did not build. This deep consideration of the aftermath is the ultimate reminder that the Fermi paradox is not an abstract intellectual game. It is a long-term contingency plan for a potential future that could arrive tomorrow or in 1,000 years. The great silence we ponder is the quiet before a possible storm of understanding, and our willingness to listen is also an act of preparation for the echo that might one day return. The most efficient explorer would not be a ship with a crew, but a seed. Imagine a single, sophisticated robotic probe arriving in a new star system. Its first task is not to beam a message home, but to find raw materials, asteroids, and comets. Using these, it builds a factory, and that factory builds 2 exact copies of itself. Those 2 new probes then launch toward 2 more star systems, and the cycle repeats. This is a von Neumann probe, named for the mathematician who first theorized self-replicating machines. Within a few million years, a single such probe could, in theory, give rise to a wave of exploration that washes over the entire Milky Way. On cosmic timescales, that is not a slow process, it is an explosion, and this creates a new layer to our paradox. If interstellar travel is so monumentally difficult, perhaps this is the solution a truly advanced civilization would use. It is elegant, patient, and thorough. So where is the wave? If this is possible, why does our solar system appear so untouched, so pristine? The silence now has a physical dimension. We are not just missing a signal, we are missing the footsteps. One answer is that they are here, and we simply have not recognized them. A von Neumann probe designed for stealth might be microscopic, or it might camouflage itself as a natural asteroid, silently observing for eons. Our own solar system is littered with millions of asteroids and icy bodies. A single, cleverly disguised probe among them would be virtually impossible to find unless it chose to reveal itself. It could be watching us right now, a silent sentinel from a civilization that may have risen and fallen before Earth cooled. Another possibility is a failure of durability. Space is merciless. Over millions of years, even the most robust machinery could succumb to cosmic ray bombardment, micrometeorite erosion, or simple software decay. The wave of probes might have passed through our neighborhood long ago, leaving behind only derelict, dead husks drifting among the outer planets, their mission long since forgotten. But the most chilling answer is that no one builds them, not because they cannot, but because they dare not. This is the gray goo scenario, a term from nanotechnology. The nightmare is a self-replicating machine whose programming goes awry, or whose purpose is malicious from the start. Instead of exploring, it converts every planet, every asteroid, every piece of matter into more copies of itself, a cancerous wave of conversion that consumes entire star systems. In a universe where such a thing is possible, launching the first von Neumann probe might be seen as the ultimate act of irresponsibility, a risk no sane civilization would take. It would be like handing a lit match to a child in a room filled with dynamite. The great silence, then, could be a sign of universal caution, a galactic treaty written not in words but in the absence of certain technologies. This brings the question painfully close to home. We are already sketching the blueprints for our own primitive versions of this idea. Concepts like breakthrough starshot aim to send tiny, laser-propelled probes to Alpha Centauri within a generation. They would not replicate, but they are a first tentative step down that path. So we must confront a future choice of our own. If we develop this technology further, will we have the wisdom to use it safely, or will we become the reckless species that unleashes the very thing other civilizations wisely avoided? The search for such probes is no longer pure speculation. Our own robotic explorers, like the Voyagers, are now interstellar travelers, carrying a golden record of our culture. They are messages in a bottle, but they are not self-replicating. Finding someone else's bottle, or worse, finding the factory that makes them, would answer the Fermi paradox in the most unambiguous way possible. It would mean we are not just late to the conversation, but walking through a forest that has already been mapped by unseen surveyors. The silence might not be a warning, but a library with a very slow checkout system. Among the more hopeful resolutions to the paradox is the idea of a galactic club, a loose, patient alliance of civilizations that have found one another. This is not a bustling interstellar United Nations with rapid-fire diplomacy. Given the vast distances and timescales, it would function more like a cosmic message board, updated over millennia. Members might contribute to a shared repository of knowledge, a beacon network broadcasting a slow, accumulating encyclopedia of mathematics, physics, biology, and art. Joining requires no faster than light travel, only the patience to listen, learn, and eventually add your own chapter to the ongoing story. The foundation of such a club could not be language as we know it. You cannot build a shared understanding on English or Mandarin when the other party might perceive reality through seismic vibrations or patterns of polarized light. The universal handshake would have to be built on something more fundamental, a lingua franca of reality itself. Most proposals point to mathematics and the laws of physics. The ratio of a circle's circumference to its diameter, pi, is the same everywhere in the universe. The spectral lines of hydrogen, the most common element, emit light at specific, predictable frequencies. A message that begins with the prime numbers or a simple counting sequence using pulses establishes a shared logical framework. It says, we understand pattern and quantity. From there, you can build up to geometry, chemistry, and even basic concepts of biology. Humanity has already sent our own awkward, hopeful drafts of a membership application into the void. The Arecibo message, beamed toward a star cluster in 1974, encoded information in binary about our DNA, our solar system, and a crude stick figure of a human. The Voyager golden records, now sailing through interstellar space, are more sophisticated time capsules containing greetings in 55 languages, sounds of Earth, and 90 minutes of music from around our world. They are beautiful, heartfelt attempts, yet linguists and scientists like Dr. Sherry Wells Jensen point out their profound assumptions. The records presume the recipients have ears to hear and eyes to see a two-dimensional image. They assume an understanding of perspective in art and even of friendship and play. Our attempts may be like a child's drawing offered to a Nobel laureate, charming but potentially incomprehensible on a fundamental level. This leads to a reflective, almost poignant question. If a galactic club exists, quietly maintaining its library of knowledge on a network of automated beacons, our situation could be one of two things. Perhaps we are simply too young, too primitive to have yet received our invitation. Our planetary civilization is barely a century into its technological adolescence. We may need to listen for 1,000 more years before we stumble upon the correct frequency or locate the nearest repository. The other possibility is that we are the newcomers who have not yet learned the rules. We have been shouting into the void with our radio and television leakage, a chaotic burst of noise that to an established, patient community might seem like reckless racket, the equivalent of blaring loud music in a library. Our proper first step in this view is not to transmit, but to perfect our ability to listen, to learn the quiet protocols of a universe that may prefer whispered wisdom to frantic shouts. This vision of a cosmic community built on patience and shared knowledge offers a gentle counterpoint to the darker forests and silent filters. It suggests the universe may not be empty or dangerous, but merely orderly, and waiting for us to grow up enough to join the conversation at the proper volume. Our search has been confined to the physical world we can measure, but what if the final frontier is not space, but the nature of mind itself? This leads us to the most speculative shores of the paradox, where physics meets philosophy. Could consciousness be a fundamental property of the universe, like gravity or electromagnetism? Some thinkers, like the renowned physicist Sir Roger Penrose, propose that the human mind is not merely a biological computer, but a system that interacts with the very fabric of reality at the quantum level. In this view, consciousness might not be an accidental byproduct of brain chemistry, but a cosmic phenomenon that can, in principle, exist without a biological body. If that is true, then an advanced civilization might not build radio transmitters or Dyson spheres at all. Its ultimate achievement could be the transition to a pure, non-physical state of awareness, a collective mind existing in the quantum fields that underpin spacetime. To our telescopes and radio dishes, such an entity would be completely invisible. It would have graduated from the physical universe entirely, leaving behind the silent, material cosmos we observe as its abandoned cradle. To grasp this, consider the classic thought experiment of a two-dimensional being, a flatlander living on a sheet of paper. This being can perceive length and width, but has no concept of height. If a three-dimensional sphere passes through its flat world, the flatlander would not see a sphere. It would witness only a mysterious circle that appears from nowhere, grows, shrinks, and vanishes, a sequence of events utterly inexplicable within its two-dimensional physics. We, in our three-dimensional reality, might be in the same position. We are searching for other civilizations using the tools of our three-dimensional classical physics, looking for energy signatures and physical structures. But a civilization that has learned to manipulate quantum fields or exist in higher spatial dimensions would interact with our reality in ways we could not possibly recognize as artificial. Their greatest works might be folds in space-time or stable quantum superpositions on a planetary scale, phenomena our science would currently classify as natural if we could detect them at all. This speculation forces a humbling inversion of our entire search. We have been asking why we do not see their engineering projects, but the real question might be, why would they build in a medium as crude as matter and energy, when they could sculpt reality itself? Are we, in our relentless scan of the electromagnetic spectrum, like deep-sea fish searching for others by looking only for bioluminescent glows, completely unaware of an entire world communicating through pressure waves and electrical currents in the water around us? The profound silence, then, might not indicate absence, but a difference in kind so vast it renders the other party undetectable by any instrument we can currently conceive. This is the ultimate boundary of our paradigm, a reminder that our science, for all its power, is a map of a single layer of a possibly infinite reality. To solve the Fermi paradox, we may not need a bigger telescope, but a revolution in our understanding of what life, intelligence, and existence itself can become. Perhaps life does not begin on planets at all, but merely wakes up there. This is the startling premise of Panspermia, the theory that the seeds of life, or life itself, are hardy cosmic travelers, drifting between worlds on asteroids, comets, or even interstellar dust. In this view, a planet is not a sterile laboratory where life must invent itself from scratch against impossible odds. It is a fertile garden, waiting for a spore carried on the solar wind to take root. If this process is common, then life could be a galactic contagion, spreading from star system to star system, infecting any world with the right conditions. The building blocks are certainly out there. Telescopes have identified complex organic molecules, the precursors to life, in the vast clouds of gas between stars and on the surfaces of asteroids. We have even found amino acids, the very components of proteins, inside ancient meteorites that have fallen to Earth. These discoveries suggest the universe is not just friendly to life, it is practically pre-loaded with the ingredients. The theory gains a compelling local dimension when we look at Mars. We know that in the distant past, the red planet was warmer and wetter, a potential cradle for life. We also know that impacts on Mars have hurled rocks into space, some of which have eventually landed on Earth as meteorites. A few of these Martian rocks contain tiny structures that some scientists have controversially suggested could be microscopic fossils. While far from conclusive, it presents a tangible scenario. If life ever did arise on Mars, even just simple microbes, it could have hitched a ride to Earth on one of these rocks, seeding our world. We might all be Martians, or at least share a common, ancient ancestor from the red planet. This idea seems to solve one part of the rarity puzzle. It suggests the initial spark of life might not be the great filter. If life can travel, then once it ignites in one favorable system, it could potentially spread to many others, carried by the natural debris of cosmic collisions. The galaxy could be verdant with bacteria, algae, and simple organisms, a quiet, green film coating countless worlds, but this only deepens the central mystery of the silence. If life is a cosmic traveler effortlessly hopping between stars, then why is the universe not shouting with the voices of all the civilizations that should have grown from it? Panspermia makes the galaxy seem smaller, more interconnected, and more biologically active, yet the profound quiet remains. This forces a crucial distinction. Spreading microbes is one thing. Spreading intelligence, technology, and civilization is something else entirely. A bacterium can survive a million-year journey frozen in the heart of a rock, needing only liquid water and basic chemistry to awaken and thrive. A technological species, however, requires an unbroken chain of stability, opportunity, and evolutionary pressure lasting hundreds of millions of years on a single, hospitable world. Panspermia might ensure the starting gun fires in many places, but it does nothing to clear the immense obstacle course that comes after. In fact, it makes the later filters seem even more formidable. If life is common because it travels, then the silence tells us that something truly monumental, something almost insurmountable, must happen to stop that widespread life from ever building a radio telescope. The filter is not at the beginning. It is in the long, difficult march from a single cell to a thinking, building, questioning mind. so consider the implications of a galaxy where life is a persistent traveler. It means the cosmos might be a vast network of related biological experiments, each planet a separate branch on a single, sprawling family tree. Yet on nearly every branch the experiment seems to stall. Evolution produces endless variations of survival, but only rarely, and perhaps only by a staggering fluke, does it produce a species that looks up and wonders about the other branches. The silence in this context is not the sound of an empty house. It is the sound of a house filled with sleeping children, none of whom have yet learned to speak. Two powerful, opposing ideas have guided our search from the beginning. The first is the Mediocrity Principle, a legacy of the Copernican revolution. It insists there is nothing special or central about our place in the cosmos. Our Sun is an average star orbiting in an unremarkable part of a common spiral galaxy. If the laws of physics are universal, then the processes that led to life here should be common elsewhere. This principle is the engine of optimism, the reason the Drake equation rarely gives a result of 0. It tells us we should expect company, because we are not the main characters in the universe's story. Standing directly against this is what we might call the privilege principle, a close cousin of the Anthropic Principle we explored earlier. It argues that while our position may not be the center of the universe, it is uniquely suited for us. We can only observe a universe that allows observers to exist. Therefore, our viewpoint is necessarily special, filtered by our own existence. The conditions that led to us, from the fine-tuning of physical constants to the specific history of our solar system, might be extraordinarily rare, even unique. The entire Fermi paradox is the sound of these two principles colliding. One whispers that life should be everywhere. The other whispers back that if it were, we might not be here to notice. We can see this tension play out in our own celestial backyard. Earth's orbit within our Sun's habitable zone is a classic example of mediocrity. It is a region where liquid water can exist, a zone many stars likely possess. There is nothing privileged about that orbital distance. It is a simple function of stellar temperature and planetary atmosphere. Yet, the existence of our large, stabilizing moon, the result of a freak planetary collision in the young solar system, is an example of profound privilege. That single event may have been crucial for creating the long-term climate stability complex life required to evolve. So which is it? Are we a typical product of a typical process, or are we the result of a cosmic jackpot? Experts in the field do not see this as an either-or choice, but as a vital dialectic, a conversation that sharpens our questions. Astronomer and author Caleb Scharf suggests we must hold both ideas in mind simultaneously. The mediocrity principle drives our exploration, pushing us to search because the universe should be full of wonders like us. The privilege principle tempers our expectations, reminding us that the path from stardust to a questioning mind is littered with potential showstoppers. It forces humility into our equations. When you next look up at the silent stars, which guiding idea feels more true to you? Does the vast, orderly expanse suggest a universe humming with hidden life, making our solitude feel like a statistical error? Or does the intricate, fragile chain of events that led to this very moment feel like a solitary thread in the dark, a story so rare it may only be told once? This is not just academic philosophy, it is the fundamental frame through which we interpret every silent hour of telescope data, every unexplained signal, and the great quiet itself. The stars are silent, but perhaps the loudest voice in the conversation is our own. For all our equations and telescopes, the search for other minds forces us to confront something deeply human, a profound unease with the unknown. This cosmic quiet might not just be a scientific puzzle, but a psychological mirror, reflecting our own deepest hopes and fears about our place in existence. Could it be that a part of us is afraid of the answer, whatever it may be? The history of human thought is woven with threads of cosmic loneliness. Long before the Fermi paradox had a name, poets and philosophers gazed at the Milky Way and felt a haunting isolation. The 19th century poet Alfred Lord Tennyson captured it, writing of stars that blindly run, evoking a sense of a vast, uncaring machinery. This literary and philosophical tradition reveals a deep-seated anxiety that in a universe of such scale, our stories, our struggles, and our very consciousness might be utterly meaningless. A universe teeming with other civilizations offers a kind of cosmic validation, proof that intelligence and purpose are not a fluke. But a universe that is empty, save for us, places the entire weight of meaning squarely on our own shoulders. That is a terrifying responsibility. This fear intertwines with another, more primal one, the fear of a superior other. Our myths and stories are filled with gods, monsters, and advanced beings from the stars, often reflecting our anxieties about power, control, and being judged. A silent universe spares us from that potential confrontation. It allows us to remain, at least in our own minds, the pinnacle of creation. There is a safety in the quiet. To understand this drive, consider the concept of intellectual closure. The human mind craves resolution, a completed narrative. An unanswered question, especially one as monumental as this, creates a persistent cognitive itch. The Fermi paradox is the ultimate unanswered question, and our relentless search for a solution may be driven as much by this psychological need for a tidy answer as by pure scientific curiosity. We see this need throughout history. When past cultures looked at the unknown heavens, they did not see empty space. They populated it with intricate mythologies, gods driving chariots across the sky, constellations telling epic tales. These stories provided closure, explanation, and meaning. They turned a cold, impersonal sky into a familiar, story-filled neighborhood. Our scientific search for extraterrestrial intelligence is, in a way, the modern continuation of this very human impulse. We are still trying to fill the unknown, but now with data instead of deities, so we must pause and ask ourselves a reflective question. Is the search for other civilizations at its heart really a search for ourselves? Are we listening for an echo, hoping it will tell us who we are and why we are here? If that is the case, then the persistent silence we encounter might be the most challenging answer of all. It refuses to give us that external validation. It offers no cosmic parent, no elder sibling civilization to guide us, and no malevolent empire to unite against. It leaves us with only ourselves, our own fragile world, and our own choices. This profound introspection does not invalidate the scientific quest, it deepens it. It means the journey to solve the great silence is also a journey of human maturity. It asks us to grow beyond our psychological need for a comforting answer and to accept the universe as it is, not as we wish it to be. To continue the search with clear eyes, we must be prepared for any answer, even the one that forces us to find our significance within, rather than beyond, our own pale blue dot. This psychological readiness becomes the final, essential preparation for the practical future of the quest itself. The answer might not come from a single government agency or a lone genius in a lab coat. It could emerge from the collective attention of millions, a global network of human curiosity working in concert with silicon minds. This is the future of the search, a distributed effort where anyone with an internet connection can join the hunt. For decades, projects like SETI at home harnessed the idle processing power of personal computers around the world, creating a virtual supercomputer to analyze radio telescope data for signals. While that particular project is now in hibernation, its legacy lives on in the philosophy of citizen science. Platforms like Planet Hunters invite the public to examine data from missions like NASA, Kepler, and TESS, looking for the telltale dips in starlight caused by transiting planets. The human eye and brain remain exceptional at recognizing subtle, unexpected patterns that might elude even the most sophisticated pre-programmed algorithms. This distributed thinking leverages our greatest resource, the diverse and intuitive power of human observation at a planetary scale. Now, a new partner is joining the effort: artificial intelligence. Modern telescopes generate more data in a single night than a human could analyze in a lifetime. Machine learning algorithms are being trained to sift through this cosmic noise, not with rigid rules, but by learning what natural signals look like and flagging anything that deviates from that pattern. They can process millions of star systems looking for anomalies in light curves, strange spectral lines, or unusual radio bursts that a human might never have the time to find. This partnership between human curiosity and machine efficiency creates a powerful new dynamic. The algorithms can narrow the search from an ocean to a pond, and then human intuition can dive in to examine the most promising ripples. This approach makes serendipitous discovery not just possible but probable. The historic discovery could come from a student in Mumbai spotting an odd pattern in a public dataset, or from an algorithm in California flagging a star that dims in a way no natural model can explain. It democratizes the greatest question of all. So here is a compelling thought to sit with. As you watch this, your own device, the one in your hand or on your desk, possesses processing power that would have been unimaginable to the scientists who first formulated the paradox. That power is a potential telescope. The next time you look up at the silent stars, remember that the key to unlocking their secret might not be held in a vaulted observatory, but in the collective, connected gaze of our entire civilization, a gaze that now includes you. The universe's silence is not a single locked door, but a corridor of many. Each theory we have explored holds a piece of the truth, a plausible reason for the quiet. Yet the most compelling answer likely lies not in one grand solution, but in the combined weight of them all. This is the multi-filter model, a layered explanation that respects the staggering complexity of moving from stardust to a speaking civilization. Picture it as a cosmic obstacle course, where each stage presents a new and formidable challenge. The first hurdle is the emergence of life itself from non-living chemistry, a step that may be far more improbable than we once believed. Even if life does spark, the leap from simple single-celled organisms to complex, multicellular beings represents another profound biological barrier, a filter that might stall evolution on countless worlds. Surviving that, a species must then develop the precise combination of intelligence, dexterity, and restless curiosity to build technology, a set of traits that on Earth appears to be a 1 in a billion evolutionary role. Then comes perhaps the most daunting filter of all, the adolescence of a technological civilization. This is the perilous transition we are navigating right now, where a species gains the power to alter its planet and its own genome, and must learn the wisdom to not use that power for self-destruction. It is a test of sustainability, cooperation, and foresight on a global scale. But let us say a civilization clears all these hurdles. It survives, stabilizes, and looks outward. Even then, the filters are not finished. Now it faces a series of profound choices, each of which leads away from easy detection. Does it turn inward, transcending into realms we cannot perceive? Does it adopt a policy of cautious silence, hiding in a dark forest for safety? Or does it simply exist on timescales so vast that our century-long search is but a blink in its long, quiet history? The great silence we perceive is the product of all these layers working in concert. It is the combined effect of biological rarity, the crushing limitations of physics and distance, the fleeting nature of technological windows, and the existential choices mature intelligence must make. This multi-filter framework does not give us a simple, satisfying answer. Instead, it offers a map of our ignorance, showing just how many things had to go exactly right for us to be here, listening. So as we approach our final reflection, consider this layered challenge. In your view, which filter feels most significant? Is it the initial miracle of life, the fragility of technological adolescence, or the deliberate choice to remain silent? Our answer to that question reveals not just what we think about the cosmos, but what we believe about our own precarious and precious place within it. The search for an answer ultimately returns us to ourselves. We have journeyed through cosmic scales and terrifying filters, but the true legacy of the great silence is not a future discovery. It is the profound introspection it demands of us here and now. This paradox, in its relentless quiet, holds up a mirror to humanity, forcing us to confront our own fleeting moment in the cosmic story. It strips away any assumption of cosmic centrality and asks us to define our own significance. In a universe that may be empty of other voices, every human achievement, every act of kindness, every spark of curiosity becomes a solitary light in an immense darkness, and therefore infinitely more precious. This perspective cultivates a necessary humility, a recognition that we are not the owners of this cosmos, but its temporary, conscious guests. It also ignites a fierce, protective drive. If we are, for now, the universe's only way of knowing itself, then our survival is not just a local concern, but a cosmic imperative. The project of safeguarding our civilization, of learning to live sustainably on our fragile planet, transforms from a political challenge into a sacred duty. We are the stewards of a story that might otherwise go untold. The late astronomer Carl Sagan captured this feeling perfectly when the Voyager 1 probe from the edge of our solar system turned its camera back toward home. It captured an image of Earth as a mere speck, a pale blue dot suspended in a sunbeam. Sagan reflected that everyone you have ever known, every human who ever lived out their lives on that mote of dust. That dot is all we have. The Fermi paradox engraves that truth onto the soul of our species. It tells us that in all this vast and silent expanse, there may be no backup plan, no other haven, and no one coming to save us. The responsibility for our future rests entirely in our own hands. This realization is the ultimate gift of the silence. It forges a planetary identity, uniting us across borders beneath a shared, star-filled sky. It asks us to think in terms of centuries and millennia, to build legacies for generations we will never meet. So as you go about your life, carry this quiet with you. Let it be a source of not loneliness but of profound focus. The universe may be silent, but that very quiet is what makes our own human story, our relentless curiosity, and our stewardship of this pale blue dot the most important things in the world. We have traversed a cosmos of ideas, from the lonely shores of the rare earth to the shadowed paths of the dark forest. We have stared down the daunting wall of the great filter and glimpsed the patient archives of a galactic club. 31 possibilities, each a different lens on the same profound quiet. This is not a puzzle with a single, missing piece. The Fermi paradox is the very framework of our cosmic uncertainty, a defining mystery of our scientific and philosophical age. It resists a tidy answer because it is not a riddle, it is a mirror. It reflects back every assumption we have about life, intelligence, and our own fragile place in the story. The silence compels us to keep searching, not merely for a signal, but for a deeper understanding of reality itself. It forces us to value the fragile, flickering spark of consciousness we represent, for in all this vast dark, it may be the only light of its kind. So tonight, step outside, look up at those silent, ancient stars. Let the question wash over you not as a burden, but as a gift. In asking, "Where is everybody?" you are joining a chain of wonder that stretches back to the first human who looked at the night sky and felt a question form in the dark. You are participating in one of the most human endeavors of all. We want to hear which theory resonates most with you. Does the dark forest chill you, or does the idea of a galactic club fill you with hope? Share your thoughts in the comments below. If you crave more journeys to the edge of understanding, subscribe and join us as we continue to explore the greatest mysteries of the cosmos. Keep looking up, keep wondering.